let's have a look at this Huffman Coding homework problem. The message for this question is rampant trump pamphlet. As the classic joke goes, you couldn't manage a full pamph. As ever, the first thing we need to do is to count the length of the message, just to make sure that in our later calculations we don't miss any letters. Let's see, you've got 5, 10, 15, 20 letters in the message. And now we need to compute our frequencies, which I'll do by tallying the letters. So we've got an R, an A, an M, a P, another A, an N, a T, an R, a U, an M, a P, an A, an M, a P, an H, an L, an E, and a T. Do we believe this? Well, let's turn the frequencies into numbers and see whether it adds up properly. So we said 2 R's, 3 A's, 3 M's, 4 P's, 1 N, 3 T's, 1 U, 1 H, 1 L, and 1 E. So let's see, we've got 1, 2, 3, 4, 7, 8, 12, 15, 18, 20 in total. So, all right so far. Now we build up our coding tree. Right, so as ever, we group the smallest 2 frequency clusters to make a new frequency cluster, adding up the frequency of the 2 pieces, and we start with each letter being its own individual frequency cluster. So we have 2 ones making a 2, another 2 ones making another 2. We've still got a 1 left, so we'll have to pair it with a 2. They make a 3. Now we have 2 2s making a 4. We have 2 3s making a 6. We have another 2 3s making a 6. We have 2 4s making an 8. 2 6s making a 12. And a 12 and an 8, bringing us to a 20. Again, that checks out. So now we're ready to assign 0s and 1s to the branches of the trees so that we can read off the codes. So let's have 0 and 1, 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 0 and 1. And now we can read off that the code for R is 0, 0, 0, 0. The code for A is 0, 0, 1. The code for M is 0, 1, 0. The code for P is 1, 0. Most common letter, shortest code. The code for N is 0, 0, 0, 1. The code for T is 0, 1, 1. The code for U is 1, 1, 0, 0. And its neighbor is 1, 1, 0, 1. The code for L is 1, 1, 1, 0. And its neighbor is 1, 1, 1, 1. Once again, let's just check this coding is prefix-free. No code is the beginning of any other code. So we've constructed a Huffman coding for this problem. It's of course not the only correct answer, but any correct answer will always produce this sequence of numbers 2, 2, 3, 4, 6, 6, 8, 12, 20. Now let's compute the message length by two different methods, just to make sure that we don't mess up. One method is simply to multiply the length of each code by the number of times it gets used, and that tells us the number of bits for that letter in the message. So 2 4s are 8, 3 3s are 9, 3 3s are 9, 4 2s are 8, 1 4 is 4, 3 3s are 9, 1 4 is 4, 1 4 is 4, 1 4 is 4, and 1 4 is 4. So what do we have? We have 5 4s being 20, we have 3 9s being 27, and we have 2 8s being 16, which is a total of 53 for the message length. Am I
63.
63. Yes, I can't add. Thank goodness for Stuart. But we would have found that anyway when we computed the message length by the other method, which is to add up the internal frequencies within the tree, the ones that tell us how often either a 0 or a 1 will be used at each node. So we certainly will visit the root node all 20 times, we'll visit this one 12 times, and this one 8 times, and each time we'll put a bit in the message. So adding these things up, we have 20, 12 and 8 will make another 20, we'll have 6, 6 and 4, which will make another 16, and we have 3, 2 and 2, which will make another 7, so we will have 20, 20, that's 40, 56 and 63. So if I hadn't noticed my arithmetic mistake earlier, I would have noticed it when I did the double check. Always worth it. Okay, now we have some true or false questions to answer for the last marks in the question. First, we are asked whether it's true that there is a prefix-free optimal coding where frequency 1 codes have different length. Now, if you look back at this picture, you'll see that all of the frequency 1 codes have length 4, but we could very easily have made them different lengths. Here we had to pair this one with a 2. If I'd paired this one with this 2, the code for N would have been shorter than the codes for U and H, and it would still have been a valid Huffman coding. So no, it's not necessary that all of those ones had to have the same length. Okay. The next thing we are asked is this. In all prefix-free optimal codings of the message, the code for P has length 2. Now that was P, the most frequently occurring symbol. And you can see that basically we were forced to group 2 4s. Well, this 4 and some other 4 to make this 8. And we were forced to put this 8 under the 20. There's no way, there was no choice about those particular groupings. Which other 4 the P was grouped with, there was a choice about, but that the 4 was below the 8 and the 8 was below the 20. No choice. So the code for P is bound to be true. Yeah, to be of length 2. So these are both true. Okay. What's next? There is a prefix-free optimal coding in which letters of frequency 3 have different length. Well, let's have a look at that. Now, there were 3 letters of frequency 3. and and there was, by that stage, some other group of 3 as well. So our 2 6s had to be made from 2 letters of length 3 and a letter of length 3 and a group with frequency 3. Sorry, not letters with frequency 3 to make a 6, and another letter of frequency 3 together with a group to make the other 6. The 2 6s had to make the 12, and then that guarantees that all of the letters with frequency 3 will have the same length. Again, there was no choice about that, so this one is false. My colour schemes have gone a bit funny. Right, next. Any proposed coding of the message with a code of length 6 or more cannot be prefix-free. Now that is clearly nonsense, because here I have a coding which is prefix-free, where the longest code length is 4. I could simply choose any code and make it length 6, and the coding would stay prefix-free. It would just no longer be optimal. So that one's nonsense. So finally we're asked, can any proposed coding of the message with a code of length 6 or more be optimal? So it says, in particular it says, any proposed coding of the message with a code of length 6 or more cannot be optimal. Let's see if we believe that. Well, the thing to do is to try and optimize, or rather, to try and build an optimal coding which has a path as long as possible. So if we were to do that, let's see, we would indeed have made a 3 by grouping this one with this 2, but the 3s would still have been the same depth down. So we can get as far as an optimal code with length 5, but length 6 will not be possible. So the last part of the question is actually true. So that's the problem finished.